Hi, everybody. I'm Matteo Casalino, PhD student at Université Claude Bernard Lyon 1 at l'IRIS laboratory under supervision of Romeo Altillon and Mohan Said Asid. I'm going to talk about an interesting connection that we think exists between a problem in access control policy management and dependency theory in relational databases. So, starting with a little bit of context and motivation. Everybody knows that IT infrastructures that offer services are often or almost, most likely organized in multiple layers. For instance, in this example, network, platform, and application. That can be more or less, but it's often the case that this is the organization. And what happens is that access control is is happening on all these layers, and it is configured via, nowadays, more and more via access control policies that are written by independent system administrators. On the other hand, users that make use of this infrastructure, they kind of make requests, and the job that these policy enforcement points at the different layers do is basically the one of letting requests go or block them right away, depending on the policy. That's the main idea of access control. And when we're looking at this scenario, what we see is that some requests are blocked at lower layers, some others are blocked, can manage to go farther, and it would be really nice if we could block them as soon as possible, enforce a kind of least privilege principle on this scenario. And the other observation that we make is that when a system administrator touches policy on one layer, as there is overlap among these policies, interdependencies in particular, what happens is that policies on other layers are typically impacted. And we would like to understand what kind of overlap this is, and if we can get rid of it in order to increase separation of concerns between different layers, basically. So the way access control policy, one way that people have proposed to model access control systems is as a mapping from access control requests to decisions, as you see here on the right of the slide. And so this policy, we call it here decision function delta. And the idea that we one characteristic of the model we want to use is that the space of all the possible requests is kind of typed, and there are different types of requests. So a type of request is a set of fields, like IP source, IP destination, port source, port destination for a firewall. And then what happens is that the space of all the possible requests is the product of the domain associated to each of these fields. Here we have a couple of examples of how such policies can look like. And the idea is that, here we use kind of a compressed notation for representing each of the possible requests and their mapping to corresponding decisions. 1 stands for allow, 0 stands for deny. But the idea is that the semantics of these tables is really you really have to think of expanding all these wildcards. It's really huge table in principle. And yeah, it's pretty straightforward. You can think about it as a relation with a functional dependency towards the decisions. So what's the problem that we were mentioning at the beginning? We try to formalize it a little more in this figure. The idea is that there is possibly overlap among request types. As you see here, the policy of the web server in the orange is on the red is kind of overlapping with the policy of the firewall in orange. And the way we think about it is that it's actually possible to model the composition, the fact that all these policies act in the same context, as there was a kind of equivalent big policy, which is the equivalent, the kind of composition of all the local ones. Therefore, the way we want to kind of fulfill the requirements I expressed in the beginning is via rewriting these local access control policies such that this idea of least privilege principle is enforced. So we want to find these delta primes in order to guarantee this first property. So each delta prime is less permissive of the corresponding delta. Plus, it's possible we would like to investigate whether we can get rid of this overlap between request types. And actually, the way the technique we want to use, or we thought about using when we look at this problem, is inspired from database theory, dependency theory, in particular multi-value dependencies, and you will see why shortly. But the idea is roughly this one. So this graph of decision function, you can think about it as a relation instance, and composition is kind of join, decomposition as kind of projection, and the idea of performing the refactoring is to do with the normalization in databases. But there are some differences. It's not plain database theory. We change things here and there, and we because of the particular context we are dealing with. And main difference is that, for instance, okay, already these request types that are basically the schema of the relations, we cannot compose them in whatever way. I mean, there is some kind of additional structure that we want to model in order to actually understand what are the joins that are allowed, basically. Plus, you will see that we need to reason in terms of non-Boolean relations. So it turns out it's not enough to have only Boolean decisions when we start thinking about composition, and you will see why shortly. And the condition for normalization in database when you think about classical databases is the one of lossless decomposition. But as we are dealing with non-Boolean relations, you will see that there is a kind of order of permissiveness on these decisions that actually means that our condition of decomposability is a little bit more relaxed, and it's like a less permissive decomposition, which is also the least privilege principle that I was talking about in the beginning. Also, as these tables are pretty big, as you can imagine, it would be simply silly to store them as they are. So what we do is that we encode them with kind of a constraint-based language. I'm not going to introduce the detail of this point because it make all the examples more messy, but you can find all the details in the paper. Anyway, the operation that we defined have corresponding algorithms that are proved to work on the kind of compact representation that we also define. There is the agenda. We already went through the introduction. I'm now going into the approach and then hopefully conclude. So what is the access control layer with this kind of thing I shown in the very beginning? So we think about an access control layer as a collection of multiple policy decision points, each of them having its own policy or decision function. And therefore, I mean, the way we formalize this is a triple, where we have a request type. I mean, all the policy decision points in the same layer share the same request type. That's the idea. So all the web servers are in the same kind of web server access control layer, as well as for firewalls and so on and so forth. And the additional thing we have here is this concept of coupling type, which is exactly what I was talking about before. I mean, it's needed in order to understand what layers can be composed, or can be joined with what others, basically. So the coupling type carries this kind of structural information about the landscape, the particular infrastructure that we are dealing with. And you see here basically the implicit rule that we defined is that the coupling type of the upper layer, when composed with a lower layer, must be embedded in the request type of the lower layer. You see it in the figure on the up right, and the kind of meaning of this coupling type, you see it depicted in this other decision function, which is the decision function of the access control layer of web servers. So you see that the coupling type for web servers is this pair of fields, IP dest and port dest. So the idea is that a particular web server is running on a particular pair, IP and port, and this identifies this particular web server within the entire layer uniquely. And then corresponding to this pair, you have its policy on the right. And you see here also why we needed to think about non-Boolean relations, because we need to model the fact that we cannot know what happens for all the possible IP addresses and ports, because some may not even make sense in a particular context, depending on network configuration and so forth. So the idea is that for, this particular example, we only know about a single web server running on this IP port, and for all the others, we have this an additional kind of undefined decision represented as a bottom symbol in the table. So that's it for the model. So what's the composition of two access control layers? It's a kind of join, except that you have additional rules that care about the structure of the request types and coupling types. So the coupling type of the lower layer becomes the coupling type of the composed layer, and then the request types are merged as a union. And then what happens to the decision function? Well, this is the join part. But since we are dealing with the non-Boolean relation, it's not a standard join. So we need to define a kind of a algebraic structure for these decisions in order to be able to compose them when two requests or two tuples, let's say in the original tables, match. And we took this distributed bounded lattice as an algebra for decisions. And you see depicted on the right there the corresponding Hasse diagram. So here an example of composition. It's pretty straightforward. We have on the left the decision function of a firewall, on the right the web server. So you see that in this case the attributes that are in. I forgot to tell something. So you can have overlap not only on. The coupling type is a kind of forced overlap. This is structural part, but also you can have overlap between request types. So in this particular example, the web server is also able to filter on IP source address of the clients, and this is where the overlap actually happens in this particular example, and this is an overlap between the two request types. And you see it reflected in the example. So whenever you have a match on IP source, IP dest, and port dest, and then you have to combine the decisions with taking, and we take actually the greatest lower bound in the lattice of decisions as a result of the combination. And you see here for the first two tuples, 1 GLB1 equals 1. Also for these two ones, these two ones, 1 GLB0 equals 0, and 1 GLB undefined equals undefined. Just straightforward if you have the lattice in mind. So what's next steps? The composition. We want to come back to the original local policies. And the composition is a kind of projection. Of course, we have to deal with the when we get rid of some column, we have to deal with the duplicates. And basically, what we do is that combine duplicate the decision associated to duplicate tuples with the least upper bound operator. And then we have first result stating that the decision functions that are decomposed via projection satisfy the least privilege principle that we were wanting from the very beginning. Always the least permissive among all the possible ones that, when recomposed, give back the original decision function. Here an example. This is the decision function of the firewall after being decomposed with the web server and decomposed back, and some decisions changed according to the least privilege principle. So we had some requests that were coming from this 3330 subnetwork that are now denied, because basically what the model realizes that there is no need for this request for be authorized already at the firewall level, because anyway they are not going through the web server anyway, because the web server was also filtering them out. Some others become undefined because, for instance, we don't know what is running on this 1112 IP address. Problem, decomposability. So we saw that we have this result guaranteeing that this decomposed policies are always the least permissive possible, least possible permissive. On the other hand, they might be too restrictive, or better said, when recomposed back, the resulting policy might be not exactly equal to the original one. And this is a problem, because it would mean that we were basically changing the global access control behavior of our system, and we don't want this. So we need a kind of decomposability condition. And this is written in red in the center of the slide. It's basically stating that when recomposing a couple of pair of layers that were decomposed via projection, we should obtain the original thing back, the original layer back, exactly as it was. And this looks pretty similar to the lossless join decomposability condition for the classical case. So how do we test this condition? Well, in the classical framework, classical relational model, there is a nice result from Fagin that links this lossless join decomposability property with the idea of multi-value dependency. So whenever you have multi-value dependencies holding on the relation, then you are sure that you can decompose it lossily. However, so what we did is that we kind of adapted this multi-value dependency idea to our case. And I mean, the biggest step in doing this is that we are dealing with non-Boolean relations, so we have to say what happens, what is a multi-value dependency equivalent in this setting, and this is the kind of definition depicted graphically. So whenever you have this pattern, I mean, you may recognize this pattern is exactly the one of MVDs. Classical MVDs is just that in the classical case, these A, B, C, D decisions can be only 0 and 1. And so what happens is that classically, if you have the first two tuples, then you need to have also the other two in your instance in order to have the MVD satisfied. what we did, we extended this, and we say, okay, the MVD, we call this interfield dependency, IFD, and it holds whenever this the decision A, GLB, decision B equals C, GLB, D. And you see that this reduces to the Boolean case, in case if you only consider 0, 1, so actually works. So you see the first two examples are basically the Boolean case, and then you see that's how it behaves for decisions different than 0 and 1. We have a theorem stating that it's the result of fagging still holds for non-Boolean relations, basically. So we have a condition, effective condition for decomposability. This is the example. So in our running example, basically we see that, of course, we can decompose with respect to the original overlapping fields that we have, IP source, IP dest, port dest, because we use them for composing the policy in the first place. On the other hand, if we try to get rid of the IP source, so we try to remove this overlap, for this particular policy, we cannot decompose. And this is a counterexample that violates the IFD. So we implemented algorithms that work on the corresponding, this kind of constraint-based representation of the policy that we have, and so what the main interesting results here is that the most complex algorithm is the one that tests the IFD, and you see in terms of complexity that it stays polynomial. On the other hand, we have a dependency on how many fields we put in join. So the more fields, the more complex. It is also, we have a dependency on the degree of overlap among the tuple descriptors that we use. So this is a link to how we actually represent these tuples. They are actually generalized tuples. So the more they overlap with each other, the more complexity we observed. To conclude, so okay, I talk about what the policy refactoring is in our view. So one problem that we didn't deal with is how to behave when we don't have decomposability. So we the algorithm just say, okay, the thing is not decomposable. Then what do you do? One idea could be to keep the algorithms with a kind of root case analysis in order to find out what's the problem and try to resolve it, to make it decomposable. And more interesting options would be to reuse existing literature in, for instance, database repair, that let actually fix kind of the database instance, relation instances based on constraints. Another interesting kind of research avenue or path would be trying to mining the dependencies instead of having the dependency, kind of the decomposition you have in mind from the very beginning. Kind of use the kind of existing approaches to mine the dependency in order to find some best possible decomposition with respect to the structure of the composed policy. Finally, it would be nice to investigate kind of generalization of this non-Boolean theory of dependencies to bring it even further, to investigate the connection with, for instance, the provenance framework, where the algebra used for giving the semantics of tuples is a commutative semi-ring, which is less constrained than our distributed lattice. And with that, I conclude. Thanks.
On a le temps pour une ou deux questions. Je vais poser une question. Tu as parlé tout à l'heure des tables qui étaient des représentations condensées les tables. Est-ce que tu peux en dire un petit peu plus sur la manière dont vous avez vous avez géré cette représentation?
Je crois que j'ai une slide avec un petit exemple. Oui, c'est là. Ah, merde, ça ne marche pas. Bon, je sais pas, ça marche. Bon, en fait, l'idée, c'est juste de représenter, on prend ça. Ah, ok. De représenter le graphe de cette fonction de décision d'une façon compacte. Et en fait, c'est vraiment à peu près ça. Du coup, au lieu de stocker chaque tuple, l'idée c'est de stocker, comme on fait en base de contraintes, une description de chaque intervalle de données représenté par chaque valeur dans la table. Du coup, par exemple, dans ce cas-là, on peut bien voir que ça suffit d'utiliser une sorte de langage à intervalles, stocker que le fait que, par exemple, pour la première tuple, on est en train de parler de IP source compris dans cet intervalle, le même pour IP dest et tout ça. Et voilà, on a utilisé un langage assez simple pour le moment, mais les algorithmes qu'on a définis sont assez génériques. Et du coup, les seules abstentions qu'on a fait sur le langage sont que ce soit possible toujours de calculer l'intersection entre deux tuples généralisés, la différence entre deux tuples généralisés et la satisfiabilité d'une formule, en fait, d'une tuple.
Merci. On peut remercier encore Mathéo.